Okay, it should be recording now, right? Yes. Okay, so the problems I chose are from the 2015 East Central North American Regional Contest. And the four problems I chose are, I guess, the four easiest problem in this set. The rings, so the 87 teams solving it. Um, this what's on the grill, 76 teams. Squawk virus is 62. And then there's a sharp drop off. Okay, the fourth easiest problem in this set, based on number of teams solving it, is 14, and then the nine teams and so on. So the four that I chose, basically there's three that are hopefully not so difficult, and then one that is significantly harder than the other three. Okay, so you can also see actually that some of these numbers. So what are these numbers? Average tries to solve, right? So basically saying that the team that solved it took four tries to solve it. Here, there's only one team that solved it. This one, seven teams that solved it, on average, it takes three tries. So here, this one, it took 2.5 tries to solve it for most teams. And then you have things like this one. Even though not many teams solved it, the teams that actually solved it doesn't take that many tries. So this is one of those problems that you would look at the stats and say, okay, it's probably not that difficult to code once you actually understand the concept of what you try to do, because the people that actually try it most of them got it, and most of them got it relatively quickly in terms of number of tries. So you can kind of look at it and say how messy something is versus how hard something is. Right? So something like this one, it might be easy, but it has a relatively high number of tries before you solve it. Anyway, the standings. This is the region that contains Ontario and New York. No, sorry, not New York. Ontario, I think Ohio, Carnegie Mellon, and a few other places, smaller places in the States, Detroit, Michigan, etc., etc. And well, the Canadian scores are usually quite good here. Waterloo was some of the best in Canada, and then it goes downhill from there. But you can see that this D, E, and I are the easiest problems. Almost every team solve some, at least one. Well, okay, there are a bunch of teams that solve nothing. Okay, so let's get started. So I think the easiest one, according to this stat, it's rings. Okay, although only 30% of the submissions are correct. So let's take a look. So you have the cross section of a tree, and the cross section of the tree is always in a rectangular grid like this. So there are n rows, m columns. And then in this grid, some part of this, the white part is empty, and then the dark parts are the tree. And then what you're going to do is you're going to classify each pixel, I guess each of these tree grid cell with a number. How is this number computed? It says, first we call all the non-tree grid squares ring 0. Okay, so everything that's outside the white ones are all zeros. Then each ring n, it's made of all those grids that have at least one ring n minus 1 as neighbor. Okay, so this sounds a little bit confusing, maybe, I don't know. But how does it work? So all of these have ring 0. And then you look at all these squares that are not white, and if it has a neighbor as 0, then it's a 1. Okay, neighboring cells are those that share an edge. So if you have a cell here, the neighbors are the 4, this one, and this one, and this one. So each cell has 4 neighbors. Okay, not the diagonals because they don't share an edge. They only share a corner. So you always have to ask in a square grid, who are the neighbors? Is it, sometimes we call it 4 neighbors, right? These 4, or is it 8 neighbors? So we, for example, maybe you consider all 8 of these neighbors. Okay, so these are sometimes called 4 neighbors, and these are sometimes called 8 neighbors. So you have to usually figure out which one is which. And in this problem, it's not 8, it's 4. So now every number, every cell here that touches, that is a neighbor of 0, it's a 1. So all of these things are 1. But this one is not a 1 because there's no, it doesn't have a neighbor of 0. Then all the things that have a neighbor of 1 will be 2, provided that, of course, it's not 0 or 1. And then all the things that have a neighbor of 2, provided it's not already been labeled, it's now 3, and so on. And you do that until you label everything. Okay, so that's basically a question. Of course, you have to produce the final output, and the final output basically looks like this. Okay, so basically you put a dot if there's nothing, and then for each tree square, you have to put the number 1, 2, 3, and so on. And then you have to do a little bit of formatting. It says that if the number of rings is less than 10, use 2 characters for each square. So here, this dot, it's represented by these 2 dots. And then this T is represented by dot 1. And then it says that if, so otherwise, if the number of rings is 10 or more, then you use 3 characters in each grid. Okay, so they don't have an example of that. But if you need to use 10 characters, right, then you, sorry, if you have the number of rings is 10 or more, then you use 3 characters. Write justify all ring numbers in grid cells and use dot to fill in the remaining characters. So here, 1, you want to print 1, but you need to use 2 spaces so that you put the 1 on the right and then put the dot in front. If a row or column does not contain a ring number, it should still be output filled entirely with dots, right? So the dot here. So that's the question, okay? For each cell, basically there are 2 parts. For each cell, you have to label it. You have to figure out what the number is, and then you have to know how to print it. Okay, if you know what the number is, printing it is not too bad, although it is still a little bit of work. So I'm going to start putting people on the spot because I think it was no that says that you think you know what to do.
Yes.
So I'm going to put you on the spot.
All right. Here I go. So first you create an array, 2-dimensional array of 100. Is it 100 by 100 at least, or 101 by 101 at least?
Okay, let me just quickly check. It's up to 100.
So it'd be 101 by 101, or just 100?
Well, okay, so number of rows and number of columns is at most 100. So it's at most 100. Okay, so it's at most this way. Wait, is it, which they say N and M, but I can never remember. N is the number of rows, okay? So the N rows and M columns, each of them is at most 100. Okay? So now you have this array, what are you going to do?
You fill it with the T's. You see in the T's for each place, just not using the spaces that it doesn't cover.
Okay, so so you're basically storing the inputs.
Yes.
Okay, so you have a grid like this, and some of them will have T's and some of them will have nothing.
Well, some of them will have dots, and the spaces that have nothing are the
Okay.
spaces we're not using.
Okay, so let's say you have something like this. Now what?
Now you need to fill out the rings. So you go first. I don't know if you should go vertically or horizontally first, but you review all the rows, and the first T you encounter, you turn into a 1, and the last T you encounter, you turn into a 1 on each vertical line.
Okay, so you start from one row at a time, and then you turn this into a 1, and then the last T, if there's a T somewhere, then you turn it into a 1.
Yes.
Okay, now what?
Then you go to the next row, turn that T into a 1, and the
And
last
then
T into
maybe,
a 1.
okay, and you do that for all the rows,
All the rows, and then then you need to do it for all the columns as well to get everything. Uh, and then
Okay,
you'll have I believe you'll have the full 1 ring completed.
okay,
And then you do the same thing for the 2s, except yeah, you find the first T you can encounter and the last T you encounter the same as before, but this time on this repetition you're turning them into 2s because the 1s are no longer T's, so you can just look for the T's that are left and turn them into 2s.
All right, okay. What do people think? What does Luke and Jenna, how do you feel about this idea?
I think that's kind of what I was thinking when I was thinking about this problem. Like I was going down, kind of scanning and then like setting everything to 0. Then when there's a T, you put it to the minimum of the surrounding blocks.
Okay, and Jenna, you have any ideas of this?
I
What do
didn't
you think?
actually finish it, but I was
Okay,
thinking
but
something
how do
with
you?
dynamic programming.
Okay, how do you feel about this algorithm?
I
that was
feel like it
described?
might take too long, but I'm not sure.
Okay, well, it's 100 by 100, so that's a 10,000. It's not a huge deal. It's probably not a huge deal in terms of time.
So it would be 2,000 at worst. Yeah.
Okay, but there's a problem. The problem is I don't think it's correct.
Oh no.
Okay, now, this is one of the problems when you read a statement like this. You look at this picture here, and you get kind of sucked into thinking that this picture represents the general input. But the problem is okay, so let's read this. So what did they tell you about the input? Okay, so blah blah blah. Decide to model a cross section of a tree on a two-dimensional grid with the interior of a tree represented by a closed polygon of grid squares given to blah blah blah. Okay, she assigns strings from the outer parts of the tree to the inner part as follows: non-tree squares of 0, and so on and so forth. And then here the input will start with a line containing 2 positive integers and m number of rows and columns, and then either it's a T or a dot. Now, are you assuming something about this tree, the input, that is not stated anywhere in this statement? Is there anything you're assuming? Right. So what is the property of this input? The only thing that it says is that this is the interior of the tree is represented by a closed polygon of grid squares. What is a closed polygon? And why is that? Why is this a problem?
A polygon is like a shape made up of sides, correct?
Yes.
Yeah. So just a
So
closed shape made up of sides that is
yeah,
represented as squares.
so usually a polygon is represented by a series of vertices, and then you connect them one at a time like this. And then, of course, you don't have something like this because you have to have squares. So maybe you have something like this, and so on. Okay. Okay. Now, if all the polygons that you see look kind of like this shape, you're good. No problem. There's nobody that says you cannot have a polygon like this. okay, or some other strange convoluted shapes. So what is the problem if you see a shape like this?
It's going to take the leftmost one and the rightmost one, but not the ones in between.
When you draw this line, so if you're looking at this row, for example, you're going to mark this one, you're going to mark this one, but then these guys here, you'll be probably completely wrong. Right?
Yep. Unless you check for, unless you're checking for a line of T's in the end of that line and the beginning of that line, and then another line of T's, and you can input another line of T's.
Yeah, but
in that
remember,
line at the beginning of that
yeah,
line.
you also have to worry about something that's really nasty. If somebody wants to make it really nasty, they can make something, I don't know, a lot of little pieces like this and then snake around back and forth, and I don't even know what I'm trying to draw, but you can stick back and forth here and the shape can get really complicated. Yes? And you know, somehow you have to be able to figure all of that out. There might be a lot of special cases that you have to deal with. You know what I mean?
Yeah, I think the algorithm still works if you're doing concurrent lines of T's, but it would get probably a lot more complicated.
Yeah, I'm also not completely sure how what is the interaction between doing the rows and doing the columns. It's probably okay, but I'm not absolutely sure.
Probably not the best solution either.
No. So let's go back to what they say, okay? So they say that non-tree grid cells are ring 0. And then if you look at the cells, so if you look at the cells that are labeled N, then it has at least one N minus 1 square as a neighbor. Okay, so let's look at this graph. Okay, I already used the word. Look at this. If you look at these squares as nodes or vertices in a graph, okay, and then the connection of, so this is what do you call it? The undirected graph, and the edges between the nodes. So nodes and graphs are the cells, and edges connect neighbor cells. Okay, so basically your graph looks like this. And so on. Okay, so you can build a graph like this.
I really got to learn how to make graphs.
Yeah, this one is fairly simple, right? It's very regular. So you build a graph like this. So the question is, why am I building a graph? What does this have anything to do with the problem? So now we're going to say that all of these, okay, so here's a graph. Okay, I'm going to erase it because I want to draw something else on top of it. But here's basically what the graph looks like. And now, what am I going to do? I'm going to call all of these cells 0. Right? Then all the neighbors, if you look at all these cells that are 0, I look at their neighbors. Some of the neighbors will be, so if I look at the neighbors of here, the neighbors are already 0. But if I look at some of these other neighbors, like this one, you have some that are already 0, but some that are not labeled. So what are they? They are my label plus 1. So all of oops. All of these neighbors of zeros that have not yet been labeled, they are ones. Oh, by the way, yeah, there's this thing from the outside, it's also one. Okay, so this is a little bit of a special case here. If you imagine that you expand this so that there's a border of 0, I guess that would make it a little bit easier, make it more uniform. Okay, so all of these are ones. Now, who are the twos? Well, you look at the neighbors of ones. If they already labeled something else, then of course they are not twos. But any neighbor of ones that are not labeled, they are twos. And then any neighbors of 2 that haven't been labeled, they are 3. Okay. Now, another way to think about it is, what does this 3 represent? Okay, what does this 3 represent? Anybody have any idea what this 3 represents?
The number of years the tree's been alive.
No, well, okay, I'm not talking about the biological meaning because this has nothing to, yeah, when we try to solve this problem, we remove ourselves from reality. That has nothing to do with the problem.
Just that it's touching 3 n minus 1 sides. That's touching 3 twos.
No, well, it doesn't matter how many 2s it touches. If it touches,
Okay.
if it touches at least 1 2, right? It has to touch at least 1 2. It doesn't matter
Okay.
which 2 it touches. It has to touch at least 1 2. So let's say it touches this 2. Okay, so it touches this 2. Okay, now what does this 2 represent? It touches a 1, right? So which one does it? That doesn't matter. You can pick either one. What does this 1 represent? It touches a 0. That's what it means. 0 just means it's not a tree. So what does this 3 mean? 3 means that if you start from the outside and try to get to this spot, it takes you 3 steps. 1, 2, 3. Right? If you go from the outside and try to hit this spot, what is this? How many steps does it take? The shortest way is 2 steps, right? 1, 2. Of course, there's longer steps like 1, 2, 3 like this, but the shortest way to get into here is 2. Does that make sense?
So are we going for shortest path here then? Is that where you're going with the graph?
Exactly. These numbers, if you say what is the shortest distance path from a node, let's call it a tree, from a tree node to get to the outside. Okay, outside of the tree. Okay, you take any node, you take any of these tree nodes, right? What is the shortest path to get out of the tree? Okay, in this case, there are multiple ways to get out in 3 steps, but the shortest way is to get to in 3 steps. And that's where the 3 comes from. And you can also even generalize and say these are 0 because it takes you 0 steps to get to the outside. You're already there. Anything that has a 1 means that you have a neighbor of 0. And that means that it takes you 1 step to get to, the outside, etc. So this is actually a shortest path problem in disguise. They didn't really tell you that very much, but that's actually, if you look at the definition, okay, let me just erase this stuff on top of it. But if you read the definition again, you start from 0, then everybody that's in distance n has to have a neighbor, at least one neighbor that's distant n minus 1. Right? So everybody that's distance 1 have to have a neighbor that's distance 0. Everybody has distance 2 has to have a neighbor that's distance 1, etc. And that's exactly the shortest distance for every node to get to the outside. Does that make sense? Okay, so what are we going to do? How are we going to code this? So shortest path, we're in shortest path. And everyone here, all the edges, have the same cost. Right? The graph is unweighted, but basically you can say every edge has same cost. So what does that mean? Breadth first search. Right? So normally how does breadth first search work? You have a start node, so you have a queue. I call it queue. And then you say queue dot push the start node. Right? There's a start somewhere that you start. And then you also set the distance of start to be 0. And you also somehow say that visited of start is equals to true. So you know that that node has been visited. Everything else is set to false, of course. Then you have this main loop that says, wow, queue is not empty. What do? You say, get the current node from the front of the queue. You pop the queue. And then for each neighbor of current, what do? If visited of neighbor is not true, so if you have never visited it before, then the distance of neighbor is equal to the distance of cur plus 1. And now you say visited neighbor is equals to true. And then also you push the neighbor. That's the classic BFS, right? And then at the end of the day, the distance, the array, I guess you call it, that stores the distance to each node from 0, from the start, will have the right numbers. Will have the right numbers populated. Now the problem is here, the not standard classic BFS has unique start points, right? But in our problem, there's not a unique start point. There's a bunch of zeros, right? There's a bunch of zeros. So what do? Actually, it's very easy. So instead of just pushing a single start, you would just put this in a loop that says for all S, which is not a tree node, so all the empty squares, then you just push all of that into the queue. Just basically do all of this with every node that is not a tree cell. And basically, this push all of the 0 vertices into the queue. And then once you get the while loop to get started, they will start labeling things, the neighbors 1, and then 2, and then 3, and so on. And this is sometimes called multi-source BFS. Okay. And then one final thing is that you have this situation here. These nodes here are 1. Why? Because this is part of the outside in. So to make things sort of easy for us to deal with, the trick is actually just to extend our inputs to have 1 extra row and 1 extra column on all sides and make them all empty. And then automatically automatically all of these things would have zeros and get pushed into the queue to start the BFS, along with all the other ones. So all of these things on the border will automatically get pushed. And so that's basically the algorithm. If I want to show you my code quickly. So I have N and M, right? The number of rows, number of columns. I have a grid, that's the input grid. And notice that I'm using 102 because I want to add an extra row, an extra column on each side. Okay, so I have to add 2 rows and 2 columns. And similarly, I have a distance, which is the place that stores the final answer. Okay, so the max D is just the maximum distance because I need to know if it's bigger than, if it's 10 or more. When I output things, we have to use 3 spaces and so on. But that's a minor thing for now. So here it is. I have a queue, and the elements of a queue is the pair of integers, row and column. Okay. Then I'm going to read my inputs, right? So I read my inputs, and I have n plus 2 rows and m plus 2 columns. If I'm in the first row, first column, last row, last column, then I just make them empty. Otherwise, I fill it in with whatever is in the inputs. At the same time, I check if the cell is not a tree cell. I set the distance to be 0, and I push it into the queue. So in C++, there's something called mPlace in many containers. So what is this mPlace? So in this container, in many containers, you have a way to insert something. So in the case of a queue is push, right? So you push something. But what is it that I have to push? It has to be an element. It has to be the right type. The right type is a pair. So I have to construct, so here has to be a pair int, right? So I have to construct a pair int, and then push it in and then put it into here. And in C++, there's a way to combine these steps. It's called mPlace. And basically what it does is it takes the parameters that you put and send it into the constructor of a pair int. So it's kind of like this. Okay, it's not exactly in this syntax, but basically it calls a constructor of the elements with these parameters, construct this pair int, and then push it. So that's a shortcut in sort of, I guess it started in C++ 11 that you can do this. Before C++ 11, you actually have to do it in 2 different steps. You have to construct a pair and then push it. Okay, so that's a C++ thing. And then otherwise, I set the distance to be -1. And for me, I'm using -1 to indicate unvisited, right? So if the distance is 0 or higher, then I'm assuming that's been visited. If it's -1, I'm assuming that it's not visited. So that's the initialization. I read the input, and I also stuff all the nodes, all the non-tree nodes with distance 0 into the queue. That's what I do. And then this is a classic BFS loop. Okay, so while queue is not empty, I pick the current one, I pop it, then I have to pick it apart because it's a pair, so I have the row and a column. And then I have to look at the 4 neighbors, and I use my standard offset array that as I go through the 4 indices, DR and DC basically would give me the 4 neighbors. This one is on top of me, so -1 for row and 0 for column. So that means it's on top. So this way is -1 and 0 for row and column. This way is 1 and 0. This way is 1 and, sorry, wait. This is 0 and 1, I mean, because I'm using DR and DC. And then this way is 1 and 0, and then this way is 0 -1. So I quite often use an array like this, the offset array, because when I look at my 4 neighbors, I can go down here and just do a for loop like this. For each of the 4 directions, the neighbor is just my current place plus the DR and DC. I wanted to make sure that I'm inside, I'm within the bounds, just in case, because if I'm at the boundaries and I try to look for the neighbors, I can actually go out bounds. So I wanted to make sure that this neighbor is actually in bounds. And if it's in bounds, then what do? I check. This says, is it visited or not? Because if the distance is already set to greater than or equal to 0, that means I have already seen it. So if it's visited, I also skip it. So if I'm in bounds and I have not visited it, then I'm going to set my distance to be the distance of the previous node plus 1, and then I'm going to push it into the queue. And then this line just have this max d that keeps track of the maximum distance I ever encounter in the whole algorithm. And then finally the outputs. This is a little bit more messy, I guess. So I loop through the array, but remember that I don't loop through the extra row and columns that I padded. Then if the distance is 0, then I either print 2 dots or 3 dots, depending on whether max d is less than 10. And then otherwise, I have to print the distance, but then I have to figure out how many space I use, and that's done by set w. And then by default, when you print numbers, it is right justified. So if I use 3 spaces and I want to print the number 5, it will print space 5. That's default. If you don't want space as the default to fill the extra spot, you can say set fill, and you can put whatever character you want, and then it will fill the empty spots with whatever character you say, in this case, a period. Okay, so in this case, the output is maybe a little bit messy. If you don't know all these C++ tricks, maybe it'll take you a lot more work to write. Maybe you'll end up writing a bunch of if-then statements. But if you know some of these things, especially set fill and set w, it's very, very useful to print things out easily. Otherwise, you're going to have to check if the number that you're printing is going to be less than 10, then you need to print 2 space first. Otherwise, if it's less than 90, if it's less than 100, then you need to print 1 space, and it's just a big mess. So learn to use set w and set fill, because that's going to save a lot of time in many cases. Okay, so that's rings. Any question?
I have like one question.
Yeah.
You said that it was a graph in the explanation, but I believe you have an array. Can it be done with an array?
Okay. So so in here, I'm actually, how do I put it? I'm not actually building any graph the way that you normally build, I don't know, a adjacency matrix or adjacency list. I am kind of using, so I'm not doing any of this. I'm using something that some people would call an implicit graph. What do I mean by that? I'm not actually explicitly saying which nodes are connected to what by storing an edge. I am using my knowledge that every node is connected to its top, bottom, left, and right neighbors. Okay, that's what I mean by a graph. So conceptually, the graph, I'm thinking about it like a graph. I'm exploring it like a graph, but I'm not actually storing it like a graph. But the way that I'm using this, writing this BFS is exactly how you would explore a graph. And that's basically down here. This is where I basically have find me all the neighbors. This is the R2, C2 is basically R plus the direction and so on.
Thank you.
Now, this is the way that I did it, but I don't know if this is actually the way that most people did it, because this is supposedly the easiest problem, and usually easiest problem are not solved by any specific algorithms, because many people don't know specific algorithms. So how else can you solve it if you know nothing about graphs? Okay, I like to think about graphs. I like to think about things that relate to theoretical concepts that are well known. But suppose you don't know anything about graphs. You don't know about breadth-first search. You know nothing. You just know how to. You just started learning how to write C++ code, and hopefully you know how to do what is a two-dimensional array. That's all you know. So what can you do? Okay. So even if you don't know graphs, how can you do this problem? Okay, so let's say this is your input. Okay. Now what are we going to do? So first thing, it's easy. It's relatively easy to fill all of these things with 0. Yes, that is hopefully not too bad. So you can go in one pass, fill in all the zeros, everything that is not a tree, you fill in 0. And actually, you should do the same trick that we did before. Okay, to make things one row and one column bigger, because that's gonna make things easier. Okay, so we did that. Now, how do you start doing labeling these things? Now we're going to look at all the t's, and for each t, if you have a neighbor you look at the 4 neighbors. If you have any neighbor that's 0, you can call it a 1, because that's the definition, right? Anybody that has, if you want to figure out if something is labeled 1, you want to know if it's a neighbor of 0. So here you go and say, okay, you look at the 4 neighbors, one of them, at least one of them is a 0, so I can say this is a 1. Then I go to this one, I can call this a 1. Go to this one, I cannot call this a 1, so I leave it. Don't do anything, okay? Don't label it 2, just call it a 1. Just leave it. This is a 1, this is a 1, this is a 1, this is a 1, this is a 1. I guess all of these, many things are 1. Okay, so in this case, a lot of things are 1s. And now you realize that you're not done because there's still some t. So now you look at all the things that got 2. So you can, again, scan all the t's and ask which t has a neighbor of 1. This one has a neighbor of 1, so you say 2. And then you do all that. If you're still not done, you look at all the t's. Who has a neighbor of 2? Those would be 3s. And just keep doing that. You can scan it multiple times. It's not the most efficient thing to do, but because this graph or this grid is so small, it doesn't matter too much, even if you have to do it multiple times. So that's so even if you don't know graph algorithms, of breadth-first search and so on, this should still work. Does that make sense? Okay, so this is I guess a graph problem, but even if you don't know it's graph, you can still kind of do it just based on the definition of the problem. Okay, so let's go to the next one. The next one that's most popular, I guess, is this, what's on the grill. It's 76 correct submissions. And it has this complicated description, but basically it says that you have a message that's written in this square grid, n by n, and n is at most 10. So again, it's not very big. Then you have something that's called a grill that has basically it's all blocking everything except for a few spots. So how do you encrypt things? You put the grill on top of this square grid, and whatever shows up, those are the letters that you write down. So you write down N, O, E, E. Those are your first four letters in the message, in the encrypted message. Then you're going to take this grill and you're going to rotate it clockwise 90 degrees. Okay, so you're going to take this and rotate it clockwise by 90 degrees. And so this comes up here, and these three becomes down here. And then, again, you look at what shows up, what are uncovered, S, R, K, and S, and then you write these down, S, R, K, and S. And then you rotate again 90 degrees, and then you write down what shows up, D, M, and Y. You rotate again, you write down what shows up. And if you rotate 4 times, if the grill is valid, you rotate it 4 times, you should grab all the characters, the 16 characters, and that would be your encrypted message, right? So send more monkeys, and the encrypted message is this, N-O-E-E, and so on. So N-O-E-E, S-R-K-S, and so on. And your job is, given the encrypted message and given the grill here, you have to produce the original message. Right? So what do you do? Right? So what you do is actually, I don't want to say it's easy, but conceptually, I guess it's easy. So let's just write this down. Okay, so let's erase, start from scratch. Server grill here. And the 4 squares that I'm allowed to use are these 4. So these square, okay, I'm kind of using the, I guess, reverse coloring scheme. The black squares are the ones that I can use. The white ones are the ones that's blocked. Okay. And then you have to figure out what is the message originally. So you have a string, right? So you have some string that's encrypted, A, B, C, D, E, F, G. I don't know, there's 16 letters in this case. And you have to start filling in. So how are you gonna fill this in? The first thing is that the first 4 letters is based on this grill here, based on these holes. Okay. And then you're gonna have to rotate this thing 90 degrees. So that becomes, you rotate it, it becomes something like this. And then you put the E, F, G, H here. So put E, F, G, H. And then you have to rotate again. And now, if you rotate again, what does it look like? It's going to look like this. Like this. So then you put the next 4 letters, I, J, K, L, and then you rotate again, and this time it's going to look like this, 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 this. Whoops, no, I screwed up. It's going to look like okay, it's going to look like here, here, and here. And then I'm going to write down MNOP, MNOP. And that would be my completed square. And then my final message would be to read this one row at a time, and that would be my answer. Okay, so is it clear how the process is? Maybe it's not clear how to code it, but if you're doing it by hand, is it clear how this process is?
Yeah.
Yes.
Okay, hang on, I need to mute all my family members, including the dog somehow. Just give me a second. Okay, so then the question is, how do you do this? I think it's probably not so difficult to figure out if you have a mask. How do you put the characters in the right place? Because basically, you just have your original, your array of characters. You have this mask. If you know that there are exactly 4 things to fill in, you just scan from left to right, from top to bottom, one row at a time, and then you start reading these characters and just saying this is E. Then whenever you see another spot to fill, you take the next character, and maybe you cross it out, and then you take the next character, and then you take the next character, and then you keep going once you rotated it. What can go wrong, right? So what can go wrong? It says that there's one additional twist. The grill given may be invalid, i.e. the holes used do not allow every location in the grid to be used during the encryption process. So when you rotate this, maybe some spot will be used multiple times and some spot will not be used at all. And so in those cases, you want to say that you cannot decrypt the message. So they give you an example. So if the grill is like this, so the only open spots are in the 4 corners, then however you rotate it, you're always only going to write into those 4 corners, so you'll never see anything. So that's kind of what you have to do. So I guess the main question is, if you know how to rotate it, then it's not that difficult to write. In fact, I'll show you the code of my solution other than the rotation. Okay, so here's my main. So I have this G, that's the grill. I read in N, I read in the grill. I just a simple for loop. And then I read in this encrypted string. And then this D is going to be my output. Okay, this D is going to be where my output character grid is. And I have K, this is an index into my encrypted string, because every time I read up a character, I would move this forward. It's basically me crossing out a character that I don't have to consider anymore. So what do? I do the following 4 times. Why 4 times? Because I do something and then at the end I call rotate, which rotates my grill. So for each time, what do? I go through my entire grill. If the grill is X, then I don't do anything because I'm blocked. If I'm out of bounds in my string, that might mean that I have too many holes in the grill, right? If the whole thing is a hose, if the whole grill is a hose, then after one rotation, or even without the rotation, I would use up my whole string. And then when I rotate, it would be wrong. So this just makes sure that I haven't gone out of bounds in my string. And this makes sure that I have not used a square more than once. So when I rotate it, I'm not going to try to write something into a spot that's already written. So if any of these conditions holds, I'm going to this part called bad. And if I jump to this part at the end, it just prints invalid GUI and exit. Otherwise, if it's not bad, then I'm just writing this letter in my string into that spot, and then I rotate. And then at the end, I just check the sanity check to make sure that I actually used all the letters, right? So I didn't, maybe somebody give me a grill that only has one hole, or maybe not even any holes, and then I didn't manage to use all the letters. So this is just a sanity check to make sure I use all those letters. And assuming everything is good, I just loop through my array and print it. That's it. So the only magic is, how do I do this rotate? So how do I do the rotate? Right, so I have n by n, and I want to take whatever pattern I have, I want to rotate 90 degrees, and then I want to end up with a new array that's rotated. So if I call this is the original G, and this is, I don't know, the new thing, let's call it G2. How do I set the values of G2 so that the values rotate, basically G rotated? So what I have to do is I have to look at any particular value. So if I look at something at I, row I, and column J, where should it come from in the original? So what does that mean, right? J, so if I look at row I, that means that this distance here is I, and this distance here is J. And this is my spot. But if I want to rotate it 90 degrees, then you have to kind of do some mental gymnastics, and you should realize that the same value, this should be I, and this should be J. If you can do kind of a sanity check, I guess. You know, if you try to rotate this thing by 90 degrees, where should it go? It should go to here, right? And then this distance here, it's this distance here, and then this distance here is this distance here. So you can do kind of a sanity check on the corners, because sometimes it's a little bit easier to understand. But generally, you have to figure out for each location in the new array, in the rotated array, where did it come from in the original one? So if you agree with this picture, right? So this here comes from here, and this here comes from here, then you'll see that this location here has row and column index. Row is actually n minus 1 minus j, because you have to start from the bottom and walk up j steps. And then the column is to move from the left I steps. And what that means is that G2 ij is actually G of n minus 1 minus j, and I like this. So my rotate code, it's right here. Okay, I use T instead of G2, but doesn't really matter. It's basically the same idea. Yeah, this is the code, right? So here in this loop, I copy. Basically, I made a new array, which is a rotated version of the old one. And then I copy this back into here, so I can reuse that original array. Does that make sense?
Yeah.
Yeah.
So this is, how do I put it? it's a very common thing, but it's always a little bit messy, right? Rotating an array, whether it's clockwise or counterclockwise, by 90 degrees is actually a very common thing that people do. But it's every time I see one of these, I have to slow down, draw the picture, and try to figure out which way it is. And that's something that you have to get familiar with and get comfortable with. Not necessarily remember exactly how the formula works, but be comfortable with how you try to derive these formulas. Okay. And also the other thing that I want to say is, even though this looks like a simple problem, especially given the number of people solving it, one of the things that I did is I didn't write everything in main. I try to hide the parts that are what I consider the messiest parts in the function, because that makes things a little bit easier to debug, right? If I need to, I can just call the function and print out the grill 4 times and make sure that the rotated answer is the right thing, right? And then, especially since they show you this example here, so you can just make sure that when you rotate this grill 4 times, it looks like this. And then if that's true, then probably your program will work. Does that make sense?
Yep.
Okay, as usual, all of these things are on my GitHub. So, okay, squawk virus. Okay, oh no, blah, blah, blah. Okay, so this is a graph problem. There's a big story, but let's just.
Ask a question.
Yes.
Did we do this one already?
Did we do this one already? Possibly.
I remember a virus question, but it was like at the beginning of when I joined. So
yeah, I might have talked about this one before. I don't know.
all right.
Yeah, it's possible. I have to go and watch all the videos to see if I said this before. I possibly. Okay, so you have a graph, and at the beginning, one user is infected. So user 0 is infected at time 0. So he got a squawk. He got one virus. Okay. Then at time 1, users 1 and 3 gets, so basically at the next time step, whoever has the squawk will send a squawk to each of its neighbors. So in the next time steps, 1 and 3 both gets a squawk. 0 doesn't get anything, okay, because it sends it away. Then in the next time steps, 0s get 2 squawk because it receives 1 from 1 and 1 from 3. 2 gets 2 squawks because it gets 1 from 1 and 1 from 3, and nobody else gets any squawks. Then in the next steps, 1 gets 4 of them. I just write the number 4 here. 3 gets 4 of them because it gets 2 from each of 0 and 2. 4 gets 2 of them from 2, and then 0 and 2 don't have any. Okay, and so on. And it keeps cycling back. So the next time step, 0 get 8, 2 get 10, right? 1 from 4 from each of 1 and 3, and 2 from 4, and then these guys don't have anything. And it just keeps on going. It keeps on going and going. And the question is, after a certain number of time steps, right? So after a certain number of time steps, how many squawks will be sent at that time step? So if I'm asking how many squawks are going to be sent at next time steps, then you'd say, what? It's going to be 8 times 2, because this 8 goes to 2, and this 10 goes to 3 neighbors, and altogether it's going to be 46. If I ask you what is the number of squawks sent in the next time step, So basically you're given this network, you're given a certain, you're told who gets infected first and how many time steps you have to follow. Then you have to determine what is the number of squawks that are sent in a certain time step. Okay, so that's the problem. And okay, so it says that it starts with the number of users, which is at least one and at most 100. The number of links or number of edges, which is basically anything from no edges all the way to complete graph. The index of the initial infected user, so there's only one that's infected. And then how many minutes? At most 9 or less. So this is very small, right? So what I mean by small, so it's 100 by 100, that's not too bad. And also there are only 9 time steps. So that's also not too bad. So because it's not so bad, we can just kind of simulate it, do it brute force. Okay, and then the only thing is to try to manage this and make sure that you don't screw up, right? So what do you do, right? One of the ways that you can do this is just have basically an array, keeping track of how many squawks there are, right? So you have an array, whatever you call it. So 0, 1, 2, how many squawks are in each spot? And at the beginning, it's 1, 0, 0, 0, like this. And then the next time step, it would look like this, right? It will be like 0, 1, 0, 1, 0, right? And then the next time step, it will be, you have to say, okay, you start with 0, 0, 0, but then for every time you see a 1 here, you say, okay, 1. 1 is here. Look at all the neighbors. So neighbors are 0 and 2, so 0 and 2 gets a 1. Then 3 has a 1. This is the other one. 0 and 2 also get another 1. So that's what it looks like. And then you go to the next step. Again, what do? You start with zeros on everything. You see a 2 here. So 1 and 3 gets a 2. And then you see a 2 here. So 1, 3, and 4 all gets a 2. So this becomes 4, this becomes 4, this becomes 2, like this, and so on. And you do 10 steps, and then that's what you get. Any question on I guess doing it by hand?
Makes sense by hand.
Okay, so how do you manage this? So you're going to store a list for each node. You're going to know who is your neighbor, and because this can be a complete graph, and this is only 100 by 100, you can use either adjacency list or adjacency matrix, doesn't really matter. So I would just use an adjacency matrix. Your graph would just be kind of like the binary matrix like this, and then the I and j, A bracket ij, would be a 1 if there's an edge from I to j, and 0 otherwise. So that's one way. That's how you would store this graph. And then basically you keep track of this, and whenever you see a 1 or whenever you see a non-zero, you just go to that node 1, and then you say, well, who are my neighbors? Well, how do you know who your neighbors are? You just look at here and you say row 1, it would look like this 0, 1, 0, 0, because that would basically 0, 1, 0, 0 would basically tell you that it's 0 is a neighbor, 2 is a neighbor, and nobody else is a neighbor. Okay, and then whenever you see a neighbor, then you just take this number and increment the corresponding neighbors in the next one. Make sure that you don't overwrite this vector, okay? Because if you start overwriting things, then you'll be in trouble. Why? Because when you look at this one, you start overwriting this one instead of over here. You overwrite this one, and then by the time you process this one, you start writing things to other places too. But in the current time step, this is still 0. And that's basically it, I guess. So if you have such a, I guess if you have such a node and you have, let's say this is VI. So this could also be kind of like a two-dimensional array, where if you want to draw it a different way, I'm kind of drawing it backwards. This could be your J, and this could be your I. So I can make it kind of a row like this. So this way would be my J, and this way would be my I, and then my first one would look like this, and then my next one would look like this, and the next one would look like this, and so on. So if I do it like this, then how would it look like? So I would have an array, so I have a graph, whether I use int or bool, doesn't matter. Okay, so with some appropriate indices, and that's my adjacency matrix that I read in. And then I would have a V, again, I would have 2 dimensions, and V0 would basically be 1, 0, 0, like this. Now, I guess for this example, this is the initial infected. If they tell you that the initial one infected is not the first user, but some other user, then you'd put that 0 and put the 1 somewhere else. But basically, the initial vector, V0, would be a vector that has all zeros except one position. And the position that's not 0 is the infected person initially. And then you would do something like this for int I equal to, well, okay, t equal, okay, I should use, what should I use? 0, t less than the t that you're given, t plus plus. You would compute v of t plus 1, it's equals to what, right? So you have to compute v of t plus 1. So compute it from v0, you have to compute v1, and from v1, you have to compute v2, and so on. So how do I compute that? So v of t0 is just, you initialize everything to be 0. So I'm kind of abusing the notation here because this is not valid C++. And then I'm going to say for all I0, I less than n, I plus plus, if, in fact, I don't even have to do that, then I'll say, and then for all neighbor j of node I, then I would say a vt plus 1j plus equals to aij. Well, actually, I don't need to do that because I already know it's a neighbor, so it's a 1. Vi. Again, then close all the squiggly braces. So what's happening? I'm saying that if I look at the previous one, so the previous entry could be all of these things. I looked at all the nodes. Whatever number of squats it is holding, whether it's 0 or 1 or any other number, whatever squats it's holding, I'm going to send it to all my neighbors in the next time step. Right? So I loop through all my neighbors in the next time step. I'm going to send it to my neighbors. So I need to up the speed t bracket I in the previous time step. So all all the squawks that node I has stored, I'm going to send it in the next time step to all my neighbors. And that basically is it. And then at the end, basically, you will be able to get from this V array the number of squawks that's held by each node at each time step, and then to figure out how many, what is the answer for whatever time step, you just look at the right row, add up the numbers of squawks that's held by everybody, and that's your answer. Does that make sense? So I want to provide a separate kind of a way of looking at things. So in this problem, t is less than 10. So it doesn't really matter. You can just do it in whichever way you want. But what if I tell you that t, I want to know the answer of t up to, I don't know, a million or something like that. Some number much bigger. Or even 10 million, even a billion. I don't. Okay, there are problems of overflow, but if you pretend that overflow doesn't exist, imagine that I want to ask you how to do it for a really large number of steps, time steps. And in this, if you do it, what we said, right, just simulate it one time step at a time, you'll never finish. Right? This is not going to work. So I want to provide a slightly different way of thinking about the problem, even though at the end of the day, it's kind of the same as what I just told you. So a somewhat different way of thinking about a problem is to, again, go back to the adjacency matrix. Okay, so the adjacency matrix says that Aij, it's 1 if I and j is an edge, and 0 otherwise. Okay. So I'm going to have this adjacency matrix A, and let's think about this V. Vi is the number of squawks at node I. And I'm going to think about this as a matrix multiplication by a vector. Okay, and then I'm going to get, let's call the result W. Okay, so what is Wi? Right? So when you multiply a matrix by a vector, you get another vector. But what exactly is Wi? I look at this particular entry, whatever that entry is. Well, Wi is the ith row of A times this column V. And what that means is that you multiply the ith row of matrix A, one element at a time, and you march this way, and then you march down the vector this way, like this. This is what Wi is. This is just standard linear algebra. Okay. Now, what's going on here? This number is either 1 or 0, right? If this is 0, then of course this term doesn't even go into the sum, because 0 times anything is 0. If it's 1, that means there's an edge from I to j, and vice versa. And I'm just multiplying 1 by the number of squawks at node j. In other words, it's just enough. I'm just adding the number of nodes in squawk, a number of squawk in node j. So what it's saying is the number of squawks in node I in the next time step is just the sum of all the squawks at node j, provided that j is the neighbor of I. And in fact, it's exactly what the thing that I was doing before. Okay, maybe we didn't think about it in terms of linear algebra, but this is exactly what's going on. That's the entry, the jth entry is just basically a number of squawks at node I, where I is all my neighbors. I'm swapping the I and j here compared to the next page. But here basically is saying that node I, the number of squawks in node I in the next time step, is just the sum of all the squawks at node j, provided that j is the neighbor of I. So what we're saying is that once you form this matrix and the vector the way that we talk about, then the vector times the matrix times the vector will give you the next vector. So maybe I'll just call it v brackets t will be the next vector, v bracket t plus 1, like this. And so if you want to go from v of 0 to v of 1, then of course you say a times this. But what if you want to go to a v of 2? Well, a squared. What if you want to go to v of t? So after t steps, whatever number of steps you want, you can actually just raise the matrix to a certain power and then multiply by the vector. And then if you make use of the fact that you have fast exponentiation algorithm, we talked about this at least once before, exponentiation. And the idea of fast exponentiation was basically that if the exponent is squared, then you just, so if you're trying to do something like a raised to the power 10, then instead of computing that, you compute a to the power 5 recursively and then take the resultant squared. And then otherwise, if you have something that's odd, then you compute a to the 10 recursively and multiply by a. And then the next step, when you compute the a to the 10, you can reduce things by half. And if you do fast exponentiation, it turns out to be logarithmic number of steps instead of linear number of steps in terms of exponent. And so that would be a faster way to compute the same thing. But in this case, because they tell you that the number of steps is only 10 or fewer than 10, then there's no need to worry about this. But if they ask you what is the number of squawks, I don't know, after a billion steps, then you have to do it this way. Anyway, so this is a kind of a graph problem that you can do it without knowing any of these math stuff, but if you know this math stuff, it might also help you think about the problem or help you implement the problem easier. Okay, any questions? Okay, what time are we at? 8:36. Okay, the next one maybe I won't be able to talk about completely, but as I said, if I look at this, the difficulty level between the first three that we talked about and the next one, it's pretty drastic. Okay, it went from 62 teams solving it to 14 teams solving it. So only I guess the top teams managed to solve. So which one is it? This is G. So if I look at G, so this is G. The first 14 teams solved it, and then nobody else solved it. Okay. So it is definitely harder. On the other hand, the first team that solved it only took 48 minutes. So maybe, and this is their, how many problems that they solved? 1, 2, 3, this is the fourth problem solved. So I guess they solved the rings, they solved squawk, they solved I, and then this is the fourth one that they solved. Okay, so let's just quickly look at what the problem is. So you have this person that owns a bunch of baking trays. They can either be 1 by 1 or 1 by 2. Okay, so 1 by 1 is this squares and 1 by 2 are these rectangles. He stores them along a 3-foot deep shelves of various lengths. So for example, if you're 5 feet long, so the height is always 3, but the width is the input. In this case, it's 5. So you want to basically figure out how many different ways you can arrange these trays, given that the size of this shelf is 3 by m, where m is at most 24. Okay, so you have at most 24 columns and always 3 rows. You're allowed to have 1 by 2 or 1 by 1. And if you use 1 by 2, you can decide to use it vertically or horizontally. You must fill this rectangle completely without anything sticking out. So you can't have things sticking out like this. You cannot leave holes, except that they will tell you that some spot cannot be used. So let's see here. Okay, the matter is complicated by the fact that often there are locations on the shelf where he does not want to put any baking trays due to leaks above the shelf, dents in the shelf surface, blah, blah, blah. So there might be spots that are illegal. So for example, here, they tell you that it's 3 by 4, and then there are 2 spots that are not available. So 3 by 4, 1, 2, 1, 2, 3. And then the 4 spots, 0.29. If I remember correctly, the way to read this, it means 0.292.44 means this one is not available because it's 0, 1, 2, 0, 1, 2, 3. So 0 and 2, then 2 and 1. These are not available. Now you have to figure out how many ways can you fit 1 by 1 and 2 by 2 pens here in this space, so that every available cell is used and nothing sticks out. So that's a question. So what should we do? So why is it that one dimension is allowed to move, and it's allowed to be sort of input, and then this dimension is always 3, right? Because if it gets too big, then it turns out to be impossible. So let's just imagine that you don't have any forbidden cells. If you're forbidden cells, it turns out it's not that hard to deal with. But let's just say that there are no forbidden cells for now. So how do we figure out how many ways can you do it? Well, what we're going to do is we're going to fill it 1 column at a time. We're going to try to fill this column here. Well, how can we fill this column? Well, we can try to fill it like this. Well, okay, well, maybe I should just say, let's just try to fill the first square. We can try to fill it like this. Or we can try to fill it like this, with this one. Or we can try to fill it like this. There are 3 possible ways we can fill this top left. Now, of course, whatever you do, you might, once you decide to fill one, let's say the red one, then you have to go down and try to fill the next one, which again has multiple choices. Okay. Everything has multiple choices, but there's an issue sometimes. Sometimes the issue is that when you, if you decide to fill it this way, then it would also not just fill this particular column, it would also partially fill the next one, which makes things a little bit tricky. So basically at every spot, you have up to 3 different things you can do. So here's a standard algorithm, I guess. The standard algorithm is for each empty spot, okay, for each empty spot, for each of the 3 ways, so answer is equal to 0. For each of the 3 ways, if it's a legal fill, so what do I mean by that? So for example, if I'm trying to fill this spot, then trying to draw something like this is not legal. Or if I'm trying to do this, but this square is not usable, then that's not legal. So you have to check all 3 ways which one is legal, and assuming that it's legal, then fill it and then do it, I guess I would just say. Just try it. Answer is plus equals to recurse. So basically recurse with at least one spot filled, and then undo the try. So you try to put something here, you recursively try things, and then you go backwards. When you're done doing your recursion, then you remove this and then you try something else. And that's the standard exhaustive search algorithm. But it turns out that if you do that, it's going to be way too slow. Oh, but anyway, if you have a recursive algorithm like this, then what you do is, if at some point, so the base case, if there are no more empty square, so I guess it shouldn't be for each empty spot, it should be, say, find next empty spot. Okay, because I'm doing recursively, not a loop. So the base case is if you have no more empty spot, then return 1. Okay, so basically it means that everything that you have done up to this point has been legal, so that means you just found one more case. And that's how you would write sort of a recursive exhaustive search algorithm, but basically it will be too slow. And the way that you can kind of see that it might be too slow is that the only concrete thing that you ever return, it's 1. So what does that mean? That means that you're literally counting every single possible ways of doing it. So if there are a million ways of doing it, you will have to do at least a million steps. And if there are more ways of doing it, then you'll be doing a lot more steps. Okay, so how do we try to get rid of this inefficiency? And the idea is to use dynamic programming. And this is I would say, much more involved dynamic programming. And the idea is that if you have filled, let's say you have managed to fill the first, whatever, k columns, in this case 4, suppose that you manage to fill the first k columns completely, then what is the best way forward? How many ways can you fill this? And if you ever recursively hit the same situation again, whenever you recursively manage to see the same situation where the first 4 columns are filled, then you don't have to do it again because you have already done it. So you just looked up this answer. But it's not so simple. Why is it not so simple? The reason is that even though you fill the first 4 columns, you might have something sticking out, or you might not, or you might have something sticking out in a different situation. So if at some point you fill the first 4 columns and this thing sticks out, and now you go ahead and do all your recursive computations, and you get a number. I don't know, from this point on, there are 40 cases. And then the next time, maybe, that you run into the same situation, but this time it sticks out somewhere else, like this. And this 40 cannot be reused because it's not the same situation. It might be completely different, the answer. So what you actually have to do is not only knowing how many rows, how many columns you have filled completely, but also what is the sort of next column you have. Because it could be that this column have a certain bit pattern, a certain pattern of which one sticks out. And basically, you have 3 things here. Each one can be sticking out or not sticking out. So there are basically 8 possibilities of sticking out. Actually 7, because if all 3 of them are sticking out, then you would consider this column filled. So basically, there's 7 ways that this next column could stick out. And if you actually consider the case where you could have sort of partially filled things like this, maybe this is sticking out like this, and then you decide to fill this one like this, then you could be actually considering sort of 2 unfilled, partially filled columns at any one time. So basically what you end up having to do is that in your dynamic programming, you have to know how many columns you have already seen, you already filled, and also what is the situation with the last 2 columns that you're trying to fill, because these last 2 columns can be partially filled. And so there's 6 spots here. There are basically 2 to the 6 different possibilities. Not all of them are possible, because you can't have something like this if you're filling 1 column at a time, because this would be empty. But anyway, it's at most 2 to the 6 or 64 different possibilities. So that's basically it, is that the state of your DP, it consists of the number of columns that you are examining, plus the bit pattern of last 2 columns. So this is the number of columns is at most 24. The number of bit patterns of last 2 columns is at most 2 to the 6. So 24 times 64, that's basically nothing. Okay, so this is definitely way harder than a standard dynamic programming problem, and it's quite involved. So I don't completely expect that you understand everything. I'll just quickly flash my code here. But basically, I have this code. I have a table that basically has the columns here, and also bit pattern that explain in the next column which ones are sticking out, and then in these bits which columns are sticking out in the second column, and then I do some bit magic to fill things in. But basically, the overall idea is look for the next empty square. This is the found one. If found is true, that means I found an empty square. Try either putting a 1 by 1. I do some bit magic, but basically I try putting 1 by 1. I try putting 1 by 2 vertically. I try putting 1 by 2 horizontally. And each one that works, I add the answer. I add the result of the recursion to the answer. And then I store the answer in my table. And then there's this other thing. If in this particular column I cannot find anything that's not covered, that means I can advance my column to the next one. And then there are a bit of mess with the bit magic here, but basically the idea is to do dynamic programming where I know how far I've gone in terms of number of columns. I fill them one at a time. And also I have to know what are the bit patterns, which squares have been filled in the last two columns. So this problem, I would say that in our region, I would not expect more than the top 10 teams to solve, maybe even fewer than that. But certainly the first three that I talked about, it should be solvable by most teams given enough time. So I would say that if you're looking for something to practice, just to get your coding skills and all that stuff going, then I would just start with those first three. If you can do this one, or if you can even understand what I talked about, that would already be a big step. Because if you haven't done a lot of dynamic programming, this is definitely way beyond the standard sort of introductory dynamic programming problems. Okay, so I guess that's all for this week. Any questions or comments? Let me stop the share.